You know, at the very heart of modern physics, there's this huge, century-old conflict. It's a real battle between two completely different and totally incompatible ideas about what reality even is. And today, we're going to dive right into the middle of that fight.
So picture this. On one side, you've got the smooth, continuous, and honestly pretty predictable universe that Einstein described with general relativity. This is what governs the huge stuff: planets, stars, galaxies. But on the other side, you've got this chunky, jumpy, and probability-based universe of quantum mechanics. That's the one that rules the absolutely bizarre world of tiny subatomic particles. It's like we have two totally different rulebooks for the same reality.
And that right there is the central mystery. How is this even possible? How can our universe be both of these things at once? This isn't just some small disagreement. It's a fundamental contradiction that has kept the world's smartest people scratching their heads for 100 years. So where do we even begin to untangle this? Okay, let's start with the world we can actually see and feel. This is Einstein's universe. It's where the laws of physics are, well, they're elegant, they're predictable, and they operate on this grand cosmic scale. Think about space and time as one single, flexible thing, like a giant trampoline fabric. General relativity tells us that really massive objects, like a star or a planet, create these deep dips and curves in that fabric. So what we feel as gravity, that's really just us rolling along those smooth curves. In this reality, everything is cause and effect. It's all nice and predictable. Let's break down this idea of relativity with a simple example. Imagine you're in a car going 60 miles per hour, and you throw a ball straight up. To you, inside the car, it just goes up and comes back down. Simple. But what about someone standing on the sidewalk? They see the ball going up and down, sure, but they also see it moving forward at 60 miles per hour. So who's right? Well, you both are. And realizing that there's no single absolute viewpoint, that changes everything. But Einstein found one thing that breaks this rule: the speed of light. It's the universe's absolute speed limit. It's always measured as the same speed, and it doesn't matter how fast you're moving. For that to be true, for the math to work, something else had to be flexible. And that something was time itself. The faster you move through space, the slower you actually move through time. Yeah, it's absolutely mind-bending, right? All right, let's take a deep breath because we're about to shift gears completely. We're leaving that smooth, predictable world behind and jumping headfirst into the strange, jumpy world of the very small. We're entering the quantum realm, where pretty much all the rules get thrown out the window. This new world was so profoundly weird that even Einstein, who actually helped kickstart the whole thing, thought it was just deeply unsettling. He famously called one of its weirdest features spooky action at a distance, this idea that two particles could be linked across vast distances and instantly influence each other. He just hated it. So what is this chunky universe, really? Well, in quantum mechanics, everything, energy, matter, it all comes in these tiny, indivisible packets called quanta. A particle can be in multiple places at once, and we can only ever talk about the probability of finding it somewhere. It's a reality built entirely on uncertainty and chance, not on clear, definite outcomes. Now, as weird as all this sounds, it really, really matters. Quantum mechanics is, no exaggeration, the foundation of our entire modern world. Without it, you wouldn't have transistors, which means no computers, no smartphones, you wouldn't have lasers or LEDs or MRI machines. All of our most essential technology is powered by this truly bizarre theory. So we've got these two different rulebooks for reality. To really understand where they clash, we need to look at the four fundamental forces that govern absolutely everything that happens in the entire universe. Here they are: gravity, the weak nuclear force, electromagnetism, and the strong nuclear force. And just look at the wild differences in their strengths and ranges. The strong force, which is what holds the nucleus of an atom together, is literally 1,000,000,000,000 times stronger than gravity. It's not even a contest. And here is the critical split. Gravity is the star player of general relativity. It's the force that shapes that smooth fabric of space-time. But the other three, the strong, weak, and electromagnetic forces, they all play by the strange, chunky rules of quantum mechanics. So this battle of theories, it's really a battle between gravity and, well, everything else. So this brings us right to the front lines, to the holy grail of modern physics, the search for a single, unified theory. A theory of everything that can write one single rulebook for the whole universe, from the tiniest particle to the biggest galaxy. And here's exactly why we need one so badly. Each theory completely falls apart precisely where we need it the most. General relativity just gives us nonsense, infinite answers when you try to apply it to the tiny, superdense center of a black hole. And quantum mechanics, it has no way to handle the immense gravity and energy of the Big Bang. They break down right at the extremes. One of the biggest ideas out there for this unified theory is something called string theory. The idea is that at the most fundamental level, everything isn't a tiny point, but a tiny vibrating string of energy. And different vibrations of these strings create all the different particles and forces we see, including gravity. The hope is that this idea can finally solve the paradox and describe both the smooth and chunky parts of our universe with one single elegant set of laws. The search is still on, and it's pushing the absolute boundaries of what we know. But it leaves us with this huge, profound question. If we finally do find this ultimate theory, what will it show us? A universe that is fundamentally predictable and set in stone? Or one that's built on pure chance and probability? The answer, whatever it is, could change absolutely everything we think we know.